For this lesson in Chapter 5, we're going to look at applications for linear programming. What we just did with the graphing gave us the ability to identify what was called a feasible region. In other words, the only area where solutions could possibly occur. So let's explore this a little bit more, and when we get to the last examples, you can see more readily how these types of procedures can be applied in a business setting. Now, notice in this theorem, existence of optimal solutions, as long as the feasible region is bounded, then you're going to have both a maximum and a minimum value exist that will definitely occur as long as the entire region is bounded. Now, if it's unbounded, and as long as the coefficients of your objective function are positive, so as long as they're positive numbers in front of your variables, then your minimum will exist, but your maximum won't. And if it turns out the feasible region is empty, if you go to graph and because of the inequalities you don't have any overlap anywhere, that means there would not be a maximum or a minimum value. So what we will do is the same thing we were doing in the earlier lesson. We're going to graph the feasible region, and then we will look for the corner points. We're going to take those corner points and we're going to put them into a table, because we're going to be given a new equation, an objective equation, where we can evaluate these corner points to determine if there is a maximum or a minimum, depending on what we're asked to find in that equation, and then we can interpret it. So let's go to the next slide, first example. Excuse me. And so we are going to do the same thing as before, except notice we have a new equation that's been provided. After we graph this and we see where the feasible region is, then we're going to minimize that region with this equation that we've been given. So let's get this feasible region onto the graph. That means this right here, if we rearrange it and we put it into slope-intercept form, we have y is greater than or equal to a negative 2x plus 4. So that tells me my y-intercept is a positive 4. It's going to cross the y-axis at 4. Since my slope is a negative 2, I'll come down to right 1. That puts me at the ordered pair 1, 2. Down to right 1. I'm now at the ordered pair 2, 0. So that line is now graphed. Because of the or equal to, it is solid. I do need to determine which way it needs to be shaded. Since y is greater than or equal to negative 2x plus 4, again, if I want to plug in 0, 0, I can go back to the original, and 0 plus 0 is greater than or equal to 4 is not a true statement. So that tells me I'm not going to shade below, I'm going to shade above this line. And these restrictions right here let me know I'm in the first quadrant. My x's have to be positives, my y's have to be positives. So this is my feasible region. Now, this thing is unbounded. What that tells me is that if it's unbounded, a maximum can't exist, but it's possible that a minimum will. In fact, the minimum should exist. So here's how we're going to determine what it would be. We have a little table here, and we're going to use the function we were given, z equals 5x plus 6y, along with the corner points that we'll identify from our graph. Now, I have a corner point here, and I have a corner point here. I actually know what they are easily because when I graphed, I know that my y-intercept was the ordered pair 0, 4, and my x-intercept was 2, 0. And the only place that a minimum or a maximum can occur is going to be at a corner point. So those are the only points I need to test. So if I plug in, I will have z equals 5 times 0 plus 6 times 4, which gives me 24 when I plug in on the top equation. And then I'll have z equals 5 times 2 plus 6 times 0, which would equal 10 when I plug in on the bottom equation. Now remember, it asked me to minimize. So I look at these two values. Which one is smaller? 10 is smaller. That means, and I'm going to use the 3 dots as a triangle, which stands for therefore, the minimum of 10, because that's the value I got when I plugged it in, occurs at the ordered pair 2, 0. Now, let's look at the next example. This time we need to maximize an equation. So this is what we'll use when we get ready to maximize. Remember, we can only maximize if it's totally bounded. And this is what we're going to need to graph. Again, we can use intercepts, or we can use slope-intercept form. If I use intercepts on this one, 4 times 0 plus 2y equals 8. So if 2y equals 8, I get y equals 4. So that means I have 0, 4 is 1 point on this graph. That's my y-intercept. Now, if I plug in 0 for y, I have 4x equals 8, so x would equal 2. So I'm going to have the ordered pair 2, 0. So 0, 4 is right here. 2, 0 is right here. That's enough for me to sketch my line. And I have to determine where my shading needs to occur. So if I use 0, 0 as my test point, if I put in 0 for x and 0 for y, 0 plus 0 is 0, and is that less than or equal to 8? The answer is yes. So that means I need to shade this part in here. This is what tells me I'm in the first quadrant. So this is my bounded region. Now, since it is bounded, that means that the possibility for a maximum does exist. Now, I have these two corner points, my 0, 4, my 2, 0. My other corner point is going to occur at 0, 0, because that's where these two intersect. So let's go to the next slide, and we're going to use those corner points and maximize this function that they gave us. Okay, we said our corner points were 0, 0. We had 0, 4, and we had 2, 0. And we're trying to maximize. Now, I'm pretty sure 0, 0 is not going to maximize it, because 8 times 0 is 0, 10 times 0 is 0. That is probably not my maximum. All right, let's plug in when x is 0, but y is 4. And that's going to give us 40. Last one, plug in when x is 2 and y is 0, and that's going to give us 16. Which one of these would be the largest number? 40. So here's what that tells us. A maximum of 40 occurs at the ordered pair 0, 4. Good job. Now, if you look at the next example, we have something very similar again, as far as this tells us we're in the first quadrant. We have 4x minus 3y is less than or equal to 9 that we'll use to get our graph, and then this is what we're asked to do to maximize this function. So let's see what happens when we graph this. If we take 4x minus 3y is less than or equal to 9, and let's try to put this into slope-intercept form. I'm going to have a negative 3y is less than or equal to, I'm going to subtract 4x from each side, so that gives me a negative 4x plus 9. And now I'm going to divide each side by a negative 3. Now I've got to be really careful. If I'm dividing by a negative, do not forget your inequality has to reverse direction. So that means I have y is greater than or equal to a positive 4/3 x, and a positive 9 divided by a negative 3 is a negative 3. So here's what I have. A y-intercept at negative 3, so at negative 3 on the y-axis, I've got a point, and if my slope is positive 4/3, I'm going to come up 1, 2, 3, 4, to the right 1, 2, 3. That tells me I'm at the point 3, 1. I'll do that again. I'll go up 1, 2, 3, 4, right 1, 2, 3, and I'm at the ordered pair 6, 5. So here's my line. And I know I'm in the first quadrant, so this is where this thing gets bounded, but I have to determine on which part of this line I'm going to shade. Since I want it to be greater than or equal to 4/3 x minus 3, let's go back and run a test point. 0, 0 is not on my line. If I go to the original and I put in a 0 minus 0, is that less than or equal to 9? And the answer is yes. So that means I need to shade on this side of my line, which is going to be this region in here. Now, I do have corner points I can identify. There are 2 of them, but be careful. What did it ask us to find? It asked us to find the maximum, or to maximize this function. What did we see if it's unbounded? If it's unbounded, there is no maximum. No reason to even take the corner points and test them, because there's not a maximum that exists. Okay, here's another one. We're going to maximize this subject to these conditions. Now again, this right here tells me it's first quadrant. So I'm going to go ahead and sketch that part. Now I have 2 inequalities that I need to put on the graph. Let's take the 6x minus 2y is less than or equal to 12. Let's look for the intercepts. So if we put in 0 for x and set this equal to 12, we're going to get a negative 2y equals 12. So y is going to equal a negative 6. That tells me 0, negative 6 is going to be a point on the graph. Now let's go back and put in 0 for y, and we'll have 6x minus 2 times 0 equals 12. So if 6x equals 12, x equals 2. So 2, 0 is also on this line. So 0, negative 6 is this point down here. 2, 0 is here. And I'm going to draw this in. And I need to determine which way this should be shaded. 0, 0 is a great test point. So if I put in 0 for x and for y, Is 0 less than or equal to 12? The answer is yes. So that tells me I need to shade on this side of this line. Now, I need to take the 3x plus y is less than or equal to 9, and also get it on the graph. So we can, again, use either method, either slope-intercept form or intercepts. If I put this in slope-intercept form, my 3x plus y is less than or equal to 9. That turns into y is less than or equal to a negative 3x plus 9. So that tells me my y-intercept is at positive 9, so I'm going to put that point up there. Since my slope is negative 3, I come down 3, right 1, and I'm at the ordered pair 1, 6. Down 3, right 1, I'm at the ordered pair 2, 3. And then down 3, right 1, I'm at the ordered pair 3, 0. Now I need to determine where that needs to be shaded. So if I go back to the original, and again I can test 0, 0. 0 plus 0 is 0, which is less than or equal to 9, which tells me I need to be shading below here. Now, be careful. If I need to be to the left of this line and I need to be below this line, that means this is my shaded region right here. And be very careful to notice we have maybe more corners than you might expect to see here. Can you determine how many corners exist? Well, there are actually 4 corners. We know we have this one, which is 0, 9. We know we have this one, which is 0, 0. But look carefully. You have this one, which is 2, 0, and then this is the one we need to find where those two equations will intersect. So let's go to the next slide where we have a little bit of room to work, and we're going to transfer over the information we have found, and we will calculate what that intersection point is for those two lines. Okay, so here's what we know. We said we have 0, 0, we have 0, 9, we have 2, 0. Now, to calculate where the intersection point was for those two lines that we graphed, we have 6x minus 2y equals 12. Remember, we can drop the inequality when we're looking for the point of intersection. 3x plus y equals 9. Now, a couple of options on how to find this. I think if I multiply the second equation by 2, that's probably my simplest way to use elimination and find where this intersection point is. You could actually also use substitution if you wanted to rearrange the second equation and solve for y. So that's going to give me 6x minus 2y equals 12 for my top equation. My bottom equation is now 6x plus 2y equals 18. Remember, everything on both sides has to be multiplied by 2. My y's cancel, and I have 12x equals 30. Now, if 12x equals 30, when I divide both sides by 12, 6 will divide into 30 5 times, and 6 will divide into 12 2 times. That means my x-coordinate is 5 halves. I need to go back and find the y-coordinate. So again, I can choose either one of these equations. If I take the second one, and I multiply 3 times 5 over 2, because I'm going to plug that in for x, plus y, set that equal to 9. That means 15 over 2 plus y equals 9. Now if I subtract 15 over 2 from each side, I'll have 9 minus 15 over 2. Remember, 9 needs to be written as a fraction with a denominator of 2. So if I multiply 9 times 2 over 2, that's going to turn it into 18 over 2. And 18 over 2 minus 15 over 2 is 3/2. I now have my corners. I'm going to have to plug these in to the equation that I was given, and remember, I was asked to maximize. And it's possible to maximize this because if you remember, when we graphed this, it was bounded. And that's the only way a maximum will exist, is if it's bounded. Now, 0 for x, 0 for y is going to give me a value of 0. If I were to plug in 0, 9, then I am going to come up with 108 when it's simplified. I don't have much space here, so I'm going to let you work that out yourself and verify. That's 108. If I plug in 2 for x, 0 for y, I come up with a value of 80. And if I plug in 5/2 for x and 3/2 for y, work carefully, you end up with 118. Guess what? That is going to be our maximum. So our maximum is 118, and that occurs at the ordered pair 5/2, 3/2. Okay? We also have this example we'll look at together. The more we practice, the better we're going to be at this. You're probably going to notice some of these equations and inequalities look familiar. That's true. We did graph these before. So if you were to look back at your work from 5.1 and 5.2, you would see that yes, we have done this before. And what we did was we multiplied this equation here by 2 to get rid of the fractions. So when we multiplied by 2, this turned into 3x minus 6y is greater than or equal to 12. And we came up with, if we used intercepts, and again, I'm just going to refer you back to look at this in 5.1, 5.2 if you need to see the work again. When x was 0, y was negative 2. When y was 0, x was 4. So if we plot that on our graph, we have 0, negative 2 right there, 4, 0 right there, and that gives us this line. And since we wanted 3x minus 6y to be greater than or equal to 12, testing 0, 0, we can see 0 minus 0 is not greater than or equal to 12, so we don't want to shade above this line. We're going to want to shade below this line. And this right here tells me I'm going to be in the first quadrant, so that's why I'm going to put the arrow where it is. Now, my second equation, if you remember, looking for intercepts, we came up with 0, 7 and 7, 0. So I'm going to put that on our graph. There's 0, 7 right there. 7, 0 occurs here. So we're going to draw that in. And since I'm testing again using 0 for x, 0 for y, 0 plus 0 is 0. 0 is not greater than or equal to 14, so I do not want to shade below this line. I'm going to want to shade above this line, the side that doesn't contain 0, 0, and that means this is my feasible region right here. Now, if I had been asked to maximize this, I would have to say there is no maximum because this is unbounded. But as long as it is unbounded, a minimum does exist. So I can minimize this. And to do so, I'm going to need to use my 2 corner points. And notice I only have 2 here. I know one of the corner points occurs at 7, 0. Because that was one of those intercepts. Now, to find out where these two intersect, if we took our 3x minus 6y equals 12 and our 2x plus 2y equals 14, and again, we could use either substitution or elimination. I'm going to multiply the bottom equation by 3, and that will give us 3x minus 6y equals 12 on top. Multiplying the bottom equation by 3 gives us 6x plus 6y equals 42. The y's cancel. We had 9x equals 54, so x equals 6. And when x was 6, if you recall, we went back, we put it in to one of these two equations that we used here, and we discovered that y was 1. And again, you can look at this work back in the earlier lesson if you need to refer to it. Now, let's minimize it. If we take 13 times 7 plus 12 times 0, 13 times 7 is 91. Now let's see what happens if we take 13 times 6 and we add 12 times 1 to it. Well, that ends up giving us 90. These are very, very close together, but since I'm trying to minimize, 90 is smaller than 91, and that means we have a minimum of 90 at the ordered pair 6, 1. That's where it will be minimized. Okay, let's see what happens on this one. We have more inequalities here, which potentially might mean we're going to have more corners, and that's okay. Since we're being asked to maximize, we know it's not going to be possible unless this is completely bounded. So let's see what happens if we try to put this on the graph. Now, this is pretty easy to find our intercepts. If I put in 0 for x, I'm going to get 4 for y. If I put in 0 for y, I'm going to get 4 for x. So 0, 4 is right here. 4, 0 is right here. So I have this first line graphed, and since I want x plus y to be less than or equal to 4, use 0, 0 as my test point. Since it's not on the line, that's going to be a true statement. So I know I'm going to shade on this side of the line, shade below it. All right, let's take x minus y is greater than or equal to negative 2. This is another one that we can solve pretty easily using intercepts. If I put in 0 for y, I'm going to get negative 2 for x. So negative 2, 0 is going to be one of the intercepts. If I put in 0 for x, then y is going to be positive 2. So I have negative 2, 0. Negative 2, 0 is right there. And then 0, positive 2 is right there. So that's what that line will look like graphed. Now, I need to determine which way that should be shaded. If I put in my test point of 0, 0, is 0 greater than or equal to negative 2? Well, the answer to that is yes. So I'm going to want to shade below this line. Okay? I have 3 more that need to be graphed. These two right here are the ones that tell me I'm in the first quadrant. So I'm on these two axes. Now I need to get x is less than or equal to 3 graphed. Since x is less than or equal to 3, it means I'm going to be crossing 3 at the x-axis. And I want to shade everything to the left of that. So I do have a bounded region. Oops. I accidentally shaded. Let me see if I can erase that part. This is not supposed to be shaded up there. because it's got to be below that line. And we have sort of an odd-shaped figure here, but I hope you can tell we have 1, 2, 3, 4, 5 corners involved in this, and yes, it is bounded, so we're going to be able to maximize it. Now, in order to get our corners, let's pick the ones that actually are intercepts. Those are the easiest ones to see. I know I've got 0, 0, and I have 0, 2. That was one of my intercepts. My x-intercept, excuse me, was at 3, 0, because that's where this vertical line crossed, which means now I have 2 that I need to calculate to see what those corners are. I need to know where this and this intersect. That's going to be this point right here. So since x was equal to 3, I'm going to have to take that and plug it into my x plus y equals 4, and I'm going to plug in x equals 3. So if 3 plus y equals 4, y has to equal 1. So that means I have a corner at 3, 1. So I have 3, 0 and 3, 1. Now we need to see where these two intersect. And the way I'll find those is I'll take x plus y equals 4 and x minus y equals -2. And I'm going to use elimination to see what I come up with. So the y's are going to cancel. I have 2x equals 2. So x will equal 1. Now I'm going to have to solve for y. If I go back to the top equation, 1 plus y equals 4. That tells me y equals 3. And if I look at my graph, that's reasonable. That looks pretty close to where this is intersecting. So now we're going to plug in and see what values we get when we use this equation that we've been asked to maximize the function with. So 0, 0 is pretty simple. That's going to give me a value of 0. If I plug in 0 for x, 2 for y, I get a value of 10. If I plug in 3 for x and 0 for y, I get a value of 12. If I plug in 3 for x and 1 for y, 12 plus 5 is 17. And if I plug in 1 for x and 3 for y, I have 4 plus 15, which is 19. This is going to be my maximum. So we have a max of 19 at the ordered pair 1, 3. All right, last two examples. And again, these are going to look familiar. These are the two that we worked on in sections 5.1 and 5.2, but we're adding an extra component. All we did in 5.1 and 5.2 is we wrote the inequalities so that we could graph and see what the feasible region was. Now, look at this last sentence. After we determine what those corner points are, it's asking us how many containers of each food should the dietitian use to meet the patient's needs and minimize the cost if this is how much food A costs and this is how much food B costs. So let's go back to what we did before. If you remember, we said since these sentences right here that contained the at least or at most, something that let us know how to write the inequalities, those would tell us how we needed to structure our sentences. Since we needed at least 10 units of additive 1, we're going to have one inequality that's based on telling us something about additive 1. We'll have one inequality for additive 2. It means since it talks about food A and food B, that's going to be our X and our Y. So X was food A, Y was food B. And when we pulled the information out of this problem, we saw, talking about additive 1, in food A, there were 2 units of additive 1. In food B, there were 2 units of additive 1. And we needed to have at least 10 units of additive 1. So that means 2x plus 2y was greater than or equal to 10. For additive 2, if we look in food A, we had 2 units. For additive 2 in food B, there were 4 units. So we have 2x plus 4y, and we needed that to be at least 12 units. So that's 2x plus 4y is greater than or equal to 12. We also said that you have to have some of food A and some of food B. So those need to be positive values. X is greater than or equal to 0, and Y is greater than or equal to 0. Now, to kind of fast forward a little bit, since we graphed this back in the earlier unit, here's what we saw. We had intercepts on this first equation of 0, 5, and 5, 0. So I'm going to draw that line in. And since we want that to be greater than or equal to 10, we tested with 0, 0. And we saw, wait, that's not true, so I don't want to shade below that line. I'm going to want to shade above. Now, my second equation, I have the ordered pair. If x is 0, y was 3. And if y was 0, x was 6. So I'm going to put that line on here. Again, testing our point 0, 0. That's not a true statement, so it tells me that I need to be shading above that line as well. So we had this unbounded region here that we found in the earlier problem. We knew that there were only 2 corners on it. Actually, we have 3 corners on this. I apologize because this is intersecting here as well. So we have, for our corners, and let me write that in for you because we're going to make a table. We have 0, 5. And then, since this is also a corner right here, that's 6, 0. What we need to know is where do those two intersect. So if we were to take 2x plus 2y equals 10, and 2x plus 4y equals 12, and I'm going to multiply everything in the top equation by a -1. That's going to change all those signs. That means my x's will cancel. I'll have 2y equals 2, so y would equal 1. Now to find the x value, I can take either one of these two equations. If I set 2x plus 4 times 1 equal to 12, 2x plus 4 equals 12, 2x is going to equal 8, and x is 2. No, sorry, x is 4. Didn't mean to confuse you there. 8 divided by 2 is 4. So we have the ordered pair 4, 1. Those are going to be our 3 corners. Here's what we haven't yet done, and that is coming up with that equation we need to try to minimize cost. So let's look at what it tells us about the cost in this last sentence. We need to know how many containers of food A and how many containers of food B, notice that's what our variables are, the X and the Y, would be needed in order to minimize the cost if food A costs $6 and food B costs $10. Well, that means my cost equation is the cost of food A, which is $6, times however many containers of food A I have, so that's 6x, plus I'll do the same thing for food B. It costs $10 times every container of food B that I will have. So that's going to be my cost function. Z equals 6x plus 10y. Now, hopefully you're seeing a more practical use of why you would need to do this in a business setting. So let's see if we can inform the dietitian how she can do this. So if we put in 6 times 0 plus 10 times 5, that's going to be 50. If we do 6 times 6 plus 10 times 0, that's going to be 36. And if we do 6 times 4 plus 10 times 1, we get 24 plus 10, that's 34. And 34 is less than 36, so here's what we should tell the dietitian. You can minimize the cost by using 4 containers of food A and 1 container of food B. Then all the conditions have been met. And our last example goes back to the Jenny and the Helen, those capes that were being manufactured. And so what we did in the last lesson is we said that because the information tells us Jenny has at most 60 hours a month to knit and at most 100 hours a month to embellish, those were going to be our 2 equations. We had one for knitting, one to embellish, and that meant that the Jenny was going to be given the variable X, the Helen model was given the variable Y. So our equations we came up with when we pulled the information out of what they told us is that for knitting we had 3x plus 5y is less than or equal to 60. That's because 3 hours of knitting on the Jenny plus 5 hours of knitting on the Helen, and she had at most 60 hours, so that means it can be less, it just can't be more, and that's why it's less than or equal to. For the embellishing, pulling those numbers out as well, we had 7 on the Jenny, so that's 7x, plus on the Helen we had 5, so that's 5y, and at most she has 100 hours, so that's less than or equal to 100. We also said you can't have negative values, so x has to be greater than or equal to 0, and so does y. And when we put this on the graph, again, you can go back and look at this if you want, we changed our scale so that we counted by 2s. Remember? To make this fit. And what we came up with was we had 0, 12 for our y-intercept and 20, 0 for our x-intercept on the first equation. And we know we want to shade below that line. Now, the second equation was the one that we ended up with the fractional value for the x-intercept. Our y-intercept was 0.20, but we wound up with like 14 2/7, which was somewhere in here. Remember, we were counting by twos. And again, when we put in our test points, we knew we wanted to shade below that. And since it's bounded by these axes, this was our feasible region. Okay? So far we're just repeating all that we had done before. We did identify some corners. This one was easy to see because it was one of our intercepts. So we had 0.12. And we know right here would be 0.0. We had this one that had the funky fraction. I actually think it was 100/7, comma 0 when we left it as an improper fraction, and that meant we had to determine where did these two equations intersect. So we took 3x plus 5y equals 60, and 7x plus 5y equals 100, multiplied the top equation by a -1, which let us cancel our y's, and -3x plus 7x was 4x, and -60 plus 100 was 40, and that gave us x equals 10. And if we plugged back in to one of these equations, let's say we had 7 times 10 plus 5y equals 100. So 70 plus 5y equals 100. If I subtract 70 from both sides, 5y would equal 30, and y would equal 6. So that gave us the ordered pair 10, 6. So at this point, we have all the same information we had from our earlier lesson. Now we're going to look at this last sentence and see if we can come up with the cost equation and give them the requested information. They want to know how many capes she should make to maximize her profit. Now remember, if I'm looking for a maximum, this has to be completely bounded. And this figure is, so we should be able to find it. And what we do know is she makes a profit of $80 on every Jenny cape and a profit of $100 on each Helen cape. So to get that cost equation, if she makes $80 on a Jenny, and a Jenny is X, that's 80X, plus $100 on each Helen is 100Y. Okay, we are ready to build our little table, and we'll get our information in there and see if we can answer this. So we have to put in our corners, and then we're going to use our cost equation, and we said it was 80x plus 100y. Okay, here are our four corners: 0, 12, 0, 0, 100/7, comma 0, and 10, 6. So let's plug in. We're going to have 80 times 0 plus 100 times 12 equals 1,200. 0, 0 is just going to be 0. Now if we put in 80 times 100/7 plus 100 times 0, 80 times 100/7 turns out to be $1,142.85 if you round to the nearest penny. So that's not going to be our winner for maximizing. Let's see what happens with 10, 6. So we'd have 80 times 10 plus 100 times 6. 80 times 10 is 800, plus 100 times 6 is 600. That's going to be 1,400, which will be our maximum. So here's what we have: a max profit of $1,400 when she makes There were 10 of the Jenny and 6 of the Helen. And that's it for Chapter 5.